Sup, nerds. So today I want to talk about some examples of integrating factors. So integrating factors are a technique to solve first order linear ordinary differential equations. So as a reminder of some of these terms, first order means that only y prime, and x appear, so there's no higher derivatives. We don't have the second derivatives, we don't have the third derivative, and so on. It's just the first derivative. And linear means that we could write it in this form. So some function times y prime plus another function of x times y plus a third function of x equals 0. So there's no y squareds or y prime squareds or square root of y's. Each of the terms y and y prime only have possibly functions of x multiplied by them. So let's get started and jump into an example. So this first example, we're not actually going to use integrating methods. It's going to be a motivating example. So we might be able to do it just from regular observations from calculus. And our differential equation is going to be x times y prime plus y equals 0. And if you stare at this for long enough, you realize that the left side is equal to the derivative of x times y. Okay, and you could check that by, if you take the derivative of x times y, we get, by product rule, it's x times the derivative of y plus y times the derivative of x, which is exactly x times y prime plus y, which is our differential equation. So if the left side of our equation is the derivative of xy, then we could just integrate both sides and get that xy equals some constant c. And then solve for y, and we get y equals c over x. And as you should do with all your differential equations, we could check this. So if we take the derivative of y, we get y prime is negative c over x squared. And plugging this back into the original differential equation, x times this derivative plus c over x gives us, well, negative c over x plus c over x, and it's 0. So it satisfies the differential equation. With a lot of differential equations, you might be given initial conditions, something that tells you the value at a single value maybe. So in this case, maybe y of 2 equals 1. And then once you have that, then you should be able to solve for any unknowns. So c is our unknown in this case, and if y of 2 equals 1, a little bit of algebra shows that c equals 2. And now we get a specific solution, y equals 2 over x, instead of the general solution, y equals c over x. So this is just a motivating example. We haven't used integrating factors yet, but hopefully with this next example, you'll see where they come into play. So for this second example, y prime plus 1 over x plus 3 times y equals 0. So the strategy is we want to multiply both sides by x plus 3. Now, we'll explain later why we do this, but after we do it, if you stare at this for long enough, it looks a lot like the previous example. And you might notice that this is equal to the derivative of x plus 3 times y by product rule and chain rule. So I suggest that you pause the video and check that if need be. And then when you're done, you'll know that if the derivative of x plus 3 times y is equal to 0, then we just integrate both sides and we get x plus 3 times y equals some constant c. And so solving for y, we get y equals c over x plus 3. And as always, you should check your work. So y prime is just going to be negative c over x plus 3 squared. And so if we plug this into the differential equation, we'll see that it indeed solves it. And again, you might be given initial conditions, say y of 0 equals 1, and you plug that in and just solve for c, and that'll give you a particular solution. So in this case, y equals 3 over x plus 3. So in this example, we multiply both sides by x plus 3. And in general, this strategy is what integrating factors is all about. So let's look at the third example. So here we have y prime plus 3y equals 6. And the strategy is we want to multiply by some function f such that the left side will look like a product rule. So f y prime plus 3y times y, which is the left side, looks like a product rule. So in order to have that, we need the derivative of f to be 3f. Okay, so again, pause and think about why that should be true. And which function has 3 times itself as its own derivative? Well, that's f of x equals e to the 3x will work. So if we multiply both sides by e to the 3x, we'll see immediately that the left side is the derivative of y times e to the 3x. And so now we just proceed like we did for the last two examples. We integrate both sides, and then we solve for y. So we're left with y equals 2e to the 3x plus c over e to the 3x, and we get that's equal to 2 plus c e to the negative 3x. And of course, check your work. So taking the derivative of this, we get the derivative of negative 3c e to the negative 3x, and then plug this in and see if it satisfies the differential equation. And you'll see that the negative 3c e to the negative 3x will cancel out with the other 3c e to the negative 3x. And we're left with just 6 on both sides. So it does satisfy the differential equation. And we might have initial conditions. So say they tell us y of 0 equals 5. Then we just solve for c and we get c is 3. And that would give us a particular solution as opposed to the general solution that we just had. Okay, so hopefully by now you have a good feel for what the general strategy is. So let's look at maybe an abstract version. So say we have y prime plus p of x times y equals q of x. And you should be able to get every first order linear differential equation like this. Okay, so once you have it of this form, we want to multiply by some function f that'll give us f times y prime plus p times f times y equals qf, and this left side we want to be the result of a product rule, f times y, and the derivative of all that. And so doing a little bit of algebra, we'll see that f should be equal to p times f. And so by the fundamental theorem of calculus, if we take f of x to be e to the antiderivative of p, then this will work by chain rule. And you could check it by taking the derivative of f. You'll see that the derivative of f is going to be f times p. So looking back at our second example, when y prime plus 1 over x plus 3 times y equals 0, in this case, it's already of the right form, and we want our integrating factor, which we'll call f, to be e to the antiderivative of 1 over x plus 3. And so you should hopefully remember from calculus that the antiderivative of 1 over x plus 3 is ln of x plus 3. So that you could find just by doing a u sub. And so our integrating factor, since e to the ln of anything is just whatever that anything is, our integrating factor is x plus 3. And that's exactly what we multiplied by to get the left side to look like a chain rule and a product rule. Okay, so let's look at maybe a more involved example now that we have this strategy. So our fourth and last example will be y prime plus 2xy equals 8x. And let's add an initial condition, y of 0 equals 5. So our integrating factor is going to be e to the antiderivative of 2x, which is just e to the x squared. So when we multiply both sides by this, we get e to the x squared y prime plus 2x e to the x squared y equals 8x e to the x squared. Now this left side is the result of a product rule and chain rule, and so when we take the antiderivative of both sides, we get y times our integrating factor, e to the x squared, equals 4e to the x squared plus c. Now this 4e to the x squared comes from a u sub. Solving for y, we get y equals 4 plus c e to the negative x squared, and that's our general solution. And then to find our particular solution, we just plug in our initial conditions and do a little bit of algebra to get c equals 1. And of course, let's check our work. So if we take our original y and we take its derivative, we get the derivative is negative 2x times c e to the negative x squared. Now if we plug this and y into the differential equation, we get negative 2x c e to the negative x squared plus 2x times 4 plus c e to the negative x squared. And then you just work out the algebra a little bit and you'll see the first and third terms will cancel and you're left with just 8x. And this is exactly what the differential equation says. So on the right side we have 8x, and so it checks out, and this is a solution. One thing to be careful of is your differential equation might not be in this right form, so you might have to do a little bit of manipulations before you try to find your integrating factor. So as an example of a differential equation that's not in the form that I was talking about, say we have 3x times y prime minus 4y equals 12. So the coefficient in front of y prime isn't 1, so we want to divide by 3x, and we're left with y prime minus 4 over 3x times y equals 12 over 3x. And then again, we solve for our integrating factor as usual, so f of x, we might want to call it as e to the negative antiderivative of 4 over 3x. And so this is just e to the negative 4/3 ln of x, which is x to the negative 4/3. So after multiplying both sides by x to the negative 4/3, then our left side is going to be the product rule of y times x to the negative 4/3. So we can take the antiderivative of the left side, and we get y times x to the negative 4/3 equals the antiderivative of the right-hand side. So the integral of 4 over x to the 7/3 is going to be 4 times x to the negative 4/3 over negative 4/3 plus some constant. And so simplifying that, it's negative 3 x to the negative 4/3 plus a constant. And so now dividing both sides by x to the negative 4/3, we get y equals negative 3 plus c times x to the 4/3. And of course, as always, we should check our work. So y prime, the derivative of this is just 4/3 c times x to the 1/3. And so plugging this into the differential equation, we get that 3x times this derivative plus 4 times the original function, the terms will cancel out and will leave us with just negative 12, which is what we have on the right-hand side. So make sure it's in the right form before you compute your integrating factor. If you like this video, make sure to smash that like button and subscribe, and if you have any questions or have any comments, just drop it below.